All right. We're happy to have Ron Do you say Artstein?
Artstein.
Artstein. Okay, here with us from USC, talking about agreement. I'll be interested if I thought maybe you'll have to throw out your slides on don't use kappa.
Well, actually, I'm really happy that I'm coming right after Bob's talk because I will respond. This is why I didn't have any questions. I will respond to to the rant on kappa because I actually use it quite a lot. But I feel I have to kind of preface my words here, my talk here. I think we actually are in agreement. I mean, we're in agreement in the sense that you don't just calculate kappa and say you're done. And I think this is probably what the rant was mostly about. That there are a lot of things kappa can't tell you, but I'm going to show that. But actually, running reliability studies and calculating agreement coefficients can actually give us a lot of information beyond just the number score. Like, oh, I got 80%, I can get myself published. And this is going to be the idea behind the talk here. So what I'm going to do, when I saw this talk was branded as a tutorial, I figured I need to give some kind of tutorial-based content. So I'm going to talk a little bit about why people calculate the kappa. And first of all, I don't want to say kappa. I'm going to say the kappa family because there's a bunch of coefficients there. And so basically, I'm going to talk a little bit about why people do this, then a bit of a tutorial content, which is how these work, which is really a very abbreviated version of content from the article in computational linguistics. And then I'm going to get into usage cases, a bunch of studies where we see how we can go beyond just the numbers and see what we can learn about the annotation process as we run agreement studies and also look at the coefficients. So why do we measure annotator agreement? Well, because we can. Agreement is something measurable, okay? Reliability, which is what we really want, is a little harder to measure. Reliability is if you take a process and you apply it again and again and again, how consistent are your results going to be? That's hard to. Well, we're not really interested in reliability. What we're really interested in is correctness, right? We create a gold standard, and for whatever purpose, whether it's for the purpose of training a system or for evaluating something, or maybe it's even just for linguistic analysis. We want stuff to be correct relative to a desired standard. I intentionally wrote there a desired standard because we don't even know if a standard exists or if a standard is even possible. And I think Bob gave a lot of examples of exactly when we don't know whether there is even a correct annotation defined according to our system. Well, we can't tell if something is correct, well, so we can say, well, at least we can see, is our instrument reliable, consistent? That's also something we can infer from something we measure. So just an illustration, an instrument can be a thermometer, and say, in this case, the mercury thermometer is a lot more reliable than the infrared thermometer because it has a much smaller margin of error. So you repeatedly measure, and you get more consistent results. Of course, it does not mean that it is correct. So that's just a quick illustration of that. Really, reliability, consistency is a minimum requirement, and we always need to take a look at the actual results to see if to evaluate whether the measurements we get actually make sense. So just to summarize the first section, reliability is the consistency of annotation in this case. It's the consistency of a process. We have to annotate the same material. This is something that that I think Bob will agree with me here, that you have multiple annotators working on the same text. We have multiple annotators because we could just say we have the same person annotate the same text again, but that's not going to work because people remember what they've done before. So I have multiple annotators. So we need multiple measures on the same text. Just like with the thermometer, you measure the same temperature several times. They have to, so you do this with different annotators because you can't have the same annotator do this. They will remember what they had done. They have to work independently. They can't talk to each other. Now, if they agree, then you can conclude that they have internalized the same scheme, sort of. You can assume that they will apply it consistently to new data if the new data are sufficiently similar to what they've seen before, and you have hope that the annotations will be correct. And the results do not generalize from one domain to another. That's basically spelling out what I said, that you assume that the data that you're going to annotate are going to be the same. If you have a bunch of movie reviews and you have a great scheme for that, now you go into sports articles, you have no idea what your scheme is going to do there. So I've been to the tutorial section. Yeah. OK, so what are these agreement coefficients that people are ranting against? And I'm really happy that Tim Miller earlier introduced coreference, because that saves me there. So this is a study where from the trains corpus. It was collected at the University of Rochester in like the early 90s. And it's about people who are planning. So it's basically dialogues between people who are planning to move. So say, why don't you take the boxcar? They're moving railway cars, OK? So why don't you load the boxcar and move it from point A to point B, and now you load the tanker over here and move it from point C to point D. And why don't you take that and move it to point E? And what does that refer to? It could refer to a boxcar or to and so we annotated this at the University of Essex like sometime around 2005. And so you end up with a bunch of expressions. OK, boxcar typically refers to boxcar. That's easy. That, well, some person says it refers to a tanker. Or another person says it refers to the boxcar. We end up with just a long list of items. And we see how much people agree. Well, let's just count how much they agree. If on 100 items they agree on 88 of them, then that agreement is 88%. Easy, and that's easy and informative, and very we know how to interpret that. That's the main advantage of just plain agreement. The problem is that you can have high agreement with low reliability, and this is actually the case of high prevalence, where Bob was saying, oh, kappa has a problem here. Well, actually, kappa does give you some, or kappa-like things do give you something useful information. So suppose we have two psychiatrists evaluating 1,000 people. I call them patients here, but they don't have to be patients. They can be people. And they say, yes, we have they agree that most of the people are not paranoid. But you got to look at who they did label as paranoid. In this case, artificially constructed, of course, notice there's not a single person that both psychiatrists agree is paranoid. Now, overall, they agree a lot on the normal case. And they're probably also correct. But the question is this annotation useful? Do you have any evidence here that they're not just picking people out of a hat, picking at random? Do you have any evidence that they are that they are able to reliably distinguish between one person and another? Whatever procedure they're using, say they're interviewing the person and answering it, filling out a questionnaire and scoring it. We have no evidence here that this procedure is actually repeatable. And this is, so reliability is a property of the procedure, of the process of annotating. And even though they agree, and they're probably correct, it's no better than just saying, well, people are not paranoid, given the evidence here. So this is the reason why we correct for chance. The reason to correct for chance is to say, we're saying, look, if people should just randomly assign, and not just randomly assign, but randomly assign from a uniform distribution, then they would agree half the time. And that is not really meaningful. And moreover, the amount expected by chance will vary depending on the scheme or on the nature of the data. So when you're evaluating people, you're just taking people, are they paranoid or not? Maybe not 99%, but a lot of the people will end up not being paranoid. So what the meaningful agreement is something better than the baseline. How much is it? We'll just look at a table, and say we have the total annotation, say what's kind of expected from chance, and the meaningful agreement is what is above chance. And formalizing, and this is exactly the same formula that Bob showed earlier for kappa and the related family of coefficients. You look at observed agreement. So observed agreement is what we counted as the actual agreement, and we somehow, through some magic, which I'll get to in a moment, we calculate what the expected value is, and then we see how much we agree above, how much agreement is above the expected value, what is the possible agreement above the value. The ratio is our agreement coefficient. How do we calculate the chance agreement? Again, very simple. And this is what is done by some of the coefficients. Actually not Cohen's kappa. These are other coefficients. These are all identical. Scott's pi, Fleiss's kappa, Siegel-Castellan's k. They're all different names for the same coefficient, which is it's of the kappa family, but it's actually not Cohen's kappa. The differences are not that important for our purposes here. So you look at the total number of judgments. You estimate the probability that a coder will pick a category at random as just the proportion of that, the proportion of that category out of the judgments. And this is you run into the problem that you do estimate the probabilities based on the annotated data. The probability that two coders would coincide is the square of that proportion. And this is a biased estimator, which is corrected by Krippendorff later on. But that's, again, with the numbers that we typically deal with, it doesn't make a huge difference. So the probability that two coders would pick, would pick the same category by chance is simply the sum over all the categories of the probability of two coders independently zeroing on that particular category. We apply this calculation to our normal and paranoid psychiatrist example, and we see that even though the observed agreement is extremely high, 99%, the expected agreement is pretty much the same, so they're working at chance level. If we have more than one coder, then we calculate, then again, what these coefficients, the same family of coefficients does is it looks at the agreement is the proportion of agreeing pairs. So if you look at the first item, we have two people say it's boxer, two people say it's tanker. There's a total of 6 pairs, so agreement is 1/3. Coder 1 and coder 3 agree, 2 and 4 agree, etc. This looks somewhat, it's sometimes difficult to see because take example B, item B, you have only one person disagreeing with the other 3, but you have 0.5% because 3 of the pairs of coders agree, 3 of the pairs disagree. The reason you do it this way is because then expected agreement is the same. It's a probability of agreement between 2 arbitrary coders. So this is the kappa family of coefficients. I'm going to go to Krippendorff's alpha, which is actually my recommendation. If you use kappa, or if you use something from the kappa coefficient family, I recommend using Krippendorff's alpha. And there are several reasons. First of all, it's unambiguous. If you say kappa, people are going to ask, which kappa? And whereas alpha, there's only one Krippendorff's alpha. There's other alphas, but they have different people's names attached in front of them. It's also a little bit more correct than the kappas because what I said earlier about the biased estimator. The main advantage of it is that it is weighted, which allows you to deal with data that's not just discrete labels that are equally different from one another. And it's related to an analysis of variance. So I'll just go quickly over what alpha is. And again, the definitive reference for this is Krippendorff's paper, which is now in its 3rd edition, I believe. Sorry, Krippendorff's book on content analysis, which is now in its third edition. So alpha is, it's a slight variation on the formula for kappa, but as you see, it's equivalent. You look at observed and expected disagreement instead of observed and expected agreement. And if you think of disagreement as 1 minus the agreement, so if agreement is percentage, so disagreement is 1 minus that, then it's equivalent to kappa. But it has the advantage that disagreement can be in units outside of the range from 0 to 1. So for example, if you look at stuff like magnitude estimation tasks, where annotators give real numbers, then you can quantify the disagreement, and I'll give you an example in a moment. And then you can have different distance metrics between the labels. So you can say some labels are closer to one another than other labels are. So for example, if I estimate something, as half or as 5 and you estimate it as 6, we're less in disagreement than if I estimated it 5 and you estimated it 12. Now, alpha is very related to alpha is related to analysis of variance. And I think it is instructive to look at what these are, because people who rant against kappa will often be very happy to accept an analysis of variance for showing certain effects. And these are actually different sides of the same thing. It's the same coin. So it's instructive to look at it, to look at how these are related. So what's an analysis of variance? And so we're looking at a single variable analysis of variance, where we have every annotated item is a different level, and we want to see how close the annotators are on the item. So we can say, for example, we have so an example that I'll give you that I'll show later on in the use cases is from Danya Scott and colleagues' paper from the last LREC, from this year's LREC, where they had people judge the likelihood of hedges in text. So say so in medical text, the doctor writes, this probably represents pneumonia. What does probably mean here? 50%, 20%, 80%? So you look at, so each individual annotated instance is a different level, a separate level, and you look at what the different annotators, marked for the items, and you want to see how close they are. So the F ratio measures the variance between the levels divided by the error variance, the variance within the individual items. And what you see, if the two are the same, then the levels are not distinct, they're random, so you assume that the annotation is random. And if F is greater than 1, then the levels are distinct and there is some sort of effect. So the items are different from one another. Just knowing that the items are different from one another is not really what we want. What we want to know is how tight the agreement is around each item. So to do this, we flip this around and change one term. If we put the error variance on top, and at the bottom, instead of the between-level variance, we put the total variance in the data sample, then when there's no error, when this number is 0, we get perfect agreement, right? There's no error. Each item has, for each item, all the annotators give exactly the same number. When the ratio is 1, then the annotation is random. They do not distinguish between the items. And the maximal value, if you make an assumption about that each item receives at least 2 annotations, then the maximal value ends up being 2. So we take this fine ratio and subtract it for 1, and we get alpha. 1 minus the error variance over the total variance is it means that when there is no error, the value is going to be 1. When it's random, when annotation is random, it's going to be 0. And with the number ranges all the way down to -1 at the maximum point, at the minimum point, I should say, So we have a coefficient which is just like kappa, ranges from where negative values mean where negative values show systematic disagreement. So alpha is 1 minus error variance over total variance, which is 1 minus observed disagreement over expected disagreement, which is the same overall formula for chance correction as the rest of the kappa family. This is just a worked out example. We have a bunch of items, 25 items. We see each item has its own associated variance. So for example, item A, all the annotators agreed that it's 7, so there's 0 variance. Some items we have some items there is disagreement. In each case, we calculate the variance. We take the mean variance per each item. That's our error term. And overall variance, we just look at all the data in the table, and the ratio is alpha. In this case, it's a constructed example. The alpha is fairly respectable. Notice that it gives us some information that's different from what the analysis variance, what the F ratio gives. What the F ratio tells us, it's that with very high probability, there is some distinction between the levels. What alpha gives us is some kind of magnitude of how much the annotators agree around the individual items. So just to summarize, I believe this is my last slide for alpha. And again, the definitive reference is in Krippendorff's book. There is the definitive reference is in Krippendorff's book. There is an abbreviated version in the CL article that I mentioned earlier. So if you want to have alpha, which is like the analysis variance, if the judgments are numerical, then you have a distance where basically the square of the difference between two judgments is the distance. This is how we capture that some judgments are closer than others. If you have all disagreements are considered equal, then you can have a very simple distance metric, which means if we have put identical labels, then we do not disagree. If we put different labels, then we do disagree. And nominal alpha is the same as kappa, save for the biased estimator difference. It's almost the same. So after presenting all of these, after presenting the kappa family of coefficients, and specifically alpha, I'm going to agree with the ranting people, saying that there is a danger here. What agreement measures, they're not like hypothesis. There's no, so they evaluate the magnitude. They say how much people agree with each other. And that's, they don't have a clear, you're not comparing two hypotheses, and you don't have a clear probabilistic interpretation of these coefficients. So, so why are people so happy to get kappa equals 0.8 and say, hey, I got a kappa 0.8. I can publish my article, and none of the reviewers is going to object. Why is that? Here's the source. Krippendorff's, the first edition of Krippendorff's book, he reports that in a study that he conducted with some other people in 1969, they had a policy of reporting on variables if their reliability is above 0.8, and we admitted variables between 0.67 and 0.8 only for drawing highly tentative and cautious conclusions. Somehow this morphed into tentative or okay when it moved to competition. But anyway, this is the source. The reason people, and this was picked up in 1996 by Carleta. Krippendorff says that content analysis researchers generally think of kappa above 0.8 as good reliability, with 0.67 allowing for tentative conclusions. This is why people in natural language processing will publish papers with kappa above 0.8, because people using this for content analysis, which is a very different task, and using different methodologies, back in the late 1960s, thought that this was a good threshold. I'll leave it at that. So after I've explained why, how these agreement coefficients work, and why we have the specific thresholds that we have for reporting, let's look at some cases and see what we can learn from agreement studies with these coefficients. So the textbook usage of conducting a reliability study is you have some written annotation guidelines, you look at generally available coders, it's important that the coders will actually, what generally available coders means is coders that are able to look at the guidelines and operate according to them, rather than the researcher and their friend who maybe have this, or the researcher and their student who have this kind of like highly internalized scheme that nobody else can reproduce. You take a representative sample of the annotation materials, and if you reach high agreement coefficient, then you have validated your annotation scheme. That's fine if you do it. But there are a lot of other things you can do. So one thing to notice is that not all coders are the same. And this is the paper from, this is the Scott et al. Paper that I mentioned earlier in the talk. You annotate hedges in medical text as a likelihood. So possible early pneumonia is possible 20% or 80%. Could represent pneumonia again. And they used many annotators. I don't have the exact number. But there were two populations of annotators, and they differed in their medical training. So basically, you can say doctors and non-doctors to simplify it. And they found a systematic difference between the annotators. Medically trained annotators tend to interpret the hedges as expressing greater likelihood. What does this mean? If you have a bunch of medical reports and you want to know what the likelihood is, and you give doctors to read this, doctors understand the text differently from, let's say, non-doctors. So now you can have put these texts on Amazon Turk or give them to your undergrad students as something to do in class, and they will annotate and they will annotate this, and they are an annotation instrument. And each instrument has, by the way, I believe they used either t-tests or analysis of variance to distinguish. They did not actually use reliability measures, but we can see here that each instrument will have its own reliability. I don't know if doctors as a group are more reliable than lay people as a group, but there clearly is a systematic difference. And can anybody guess which group is more correct in their interpretations? I'm guessing the doctors, but it's not based on any statistics. I'm just thinking that doctors are probably better at understanding things written by doctors and for doctors. But it's just a guess, and this is an important thing that we need to do when we run our annotation studies. And I think almost everybody touched upon this before. Almost everybody who talked about annotation touched on it before us. We need to apply some kind of level of common sense to see, are the annotations that we're getting, okay, they're reliable, but are they useful? Are they correct? Coders agree to different extents also. Here is a set of annotation studies that we ran. We had 3 data sets, each annotated by 4 coders, and they get to some kind of, they get to a certain level. So, in one case we got 0.76 alpha. These are all measures of Krippendorff's alpha. And another case, other cases we got 0.53. What's interesting here is that if you throw away the outlier, throw away just one coder who does not agree with, who agrees least with the group as a whole, you get much higher. You get much higher reliability, or reliability is the wrong term. You get much higher coefficient value. And the range, if you look at all the subgroups, typically the most disagreeing group and the most agreeing group would be just a pair. There is a very wide range. If you have just 4 coders, the pair of coders that disagree the most and the pair of coders that disagree the least are quite distant from one another. And so there are methods. Hayes and Krippendorff propose a method to evaluate confidence intervals for kappa by sampling and by resampling the same data. But these only generalize over the items annotated. And we don't have a way to generalize over coders. And I don't think there is a way. If I have just 4 coders, I don't think there is a way to say, well, how likely is a 5th coder from outside the pool, how likely are they to agree with us? So the best advice I can say here is we just got to use a lot of coders. But this is a problem, that you only get information for the coders that you for the coders that you've tested. What can we learn from disagreements? So here's a study that we concluded where you match utterances to dialogue acts. So I think I'll give a little, because since I'm not sure how many people here are familiar with dialogue systems, typically a dialogue act is a simplified representation of the content of an utterance that an agent can act upon. So here we have an agent, her name is Amani, and people talk to her and she responds. And she actually processes spoken language. And in this particular case, you ask her about it. It's done for training, and you ask her. A user comes, and he's supposed to ask her about some kind of incident that happened with some sniper fire somewhere. It's a military scenario, and the idea is to train people how to ask questions. So you train people so people come and they train against these people how to interview people and extract information from people through interview. And she processes so the character processes spoken language, but her understanding is limited. So basically what we're doing, so the way she works is she has a fixed set, a fairly large but fixed set of things she can understand. These are specific dialogue acts. And then there's a statistical classifier, which every spoken utterance maps it to one of the dialogue acts. Or it can say also, I don't understand this. And then she will act based on that. And the question we had here is, so then we ran her. We had her talk to 16 people in this case, collected a bunch of a bunch of user utterances, and the question we had is, how well do the dialogue act, how well does her interpretation scheme represent what people actually want to say? How am I doing in time? So I just don't remember when I started. Okay.
About 15 minutes.
Another 15 minutes. Okay, that's good. Okay. So the instruction was extremely simple. So basically, tell the annotators, match each user utterance to the most appropriate player speech act, and if none is appropriate, match it to unknown. So here are some examples. Somebody came up to the character and asked, are you a school teacher? And this is something that she knows about, something she can understand, because she has a yes-no question specified, do you work as a teacher? So all the 3 annotators agreed, yes, this is the correct representation. Thank you and good night. She has a way of generically representing thanks, a generic speech act to represent I'm ending the dialogue now. She does not have a way to combine these two together. That's a deficiency of the scheme. And this is a case where one annotator decided, well, this is probably best mapped to the thanks. Another best maps to I'm finishing the dialogue now. So that's a case of disagreement. Some other cases of disagreement are a question, can you tell me about the sniper? This shows multiple levels of disagreement. First of all, can you tell me is literally a yes-no question. Can you tell me about the sniper? Yes, I can. No, I can't. Typically, people will understand it as an information-seeking question. Tell me something. What can you tell me? Which is represented in the dialogue act scheme. It's represented as WH questions. So one interpreted as an information-seeking question, another interpreted as a yes/no question. Yet another said this is not close enough to any of the dialogue acts in her representation that. So I prefer to have her deal as if she does not understand the question. So these are the kinds of agreements and disagreements we see in the corpus. What do reliability coefficients tell us here? We calculated reliability on 3 features. One is this fully specified dialogue act. Another is the dialogue act type. That's basically just chopping off some information. And the third thing is whether the dialogue act is in the domain or not. So just putting everything that people thought she can understand in one category, and another category, things people thought she could not understand. Now, if you look at the observed disagreement, which again, observed agreement is something that's easy to interpret. Necessarily, people are going to agree more about whether something can be understood or not than on what exactly it means, because one is derived from the other. But this is, however, expected disagreement is going to be lower because now when you have a binary classification, then the chance is higher. So what happens here is that reliability, first of all, because the instructions were so simple, the instructions were basically one line: match it to the closest dialogue act. If it's not close enough, match it to unknown. So this really measures how straightforward the task is. If you just let people say, okay, annotate it to the best of your understanding, is this something easy or hard to do? And later when we had some more explicit guidelines, the reliability improved. But you see that the question, is it in the domain or not, is less reliable, and this is the importance of, this is where chance correction does give you useful information. It shows that this is a less straightforward task. So the task of identifying what the utterance means is, it has, say, 0.50 reliability, whatever that means, but the task of saying, is this close enough to, is what the person said, is it close enough to what the character could understand, or does she need to deal with it as something she does not understand? This is a much more difficult task, and this is why we see lower agreements. And finally, the subsequent analysis of the disagreements showed that we believed. So now we just looked at all the disagreements between the coders. So this no longer has to do with the coefficients, but it has to do with the data that we got from the agreement study. And we found that we estimated that about 80% of the user utterances could be represented by the scheme with proper expansions, and a follow-up study found that it was about correct. Another study with a virtual character. Here we have a character that responds to people. It's a simple question-answering character, and you ask something and can respond either with an on-topic response, like, it's a military sergeant, and you ask him, what's your name? I'm Sergeant Starr. What are you wearing? I'm wearing my, I don't know, night vision goggles. When's your birthday? He doesn't understand this question, so he's going to get something. Why don't you ask me about something else? That's an off-topic response. And then we rated, we had 4 raters rate the coherence. So how appropriate is this response in context? And this is what we found. First of all, we found that it's very good. So the green responses are the on-topic ones, the red responses are off-topic ones, and we're very happy that most of the responses are 5, are very highly coherent. Good. But looking at the reliability, I find that overall, the annotators are reliable. And for the on-topic responses, they are reliable also. But for the off-topic responses, they're extremely unreliable. So barely above chance. What does this mean? Well, first of all, this goes back to item bias, or item difficulty, I should say. Some things are just easier to annotate than others. If the character says, these are my night vision goggles, it's fairly easy to say, is this a good response to what the person asked, or is it a bad response to what the person asked? If the character says, why don't you ask me about something else? Or, hooah, which is what someone thinks he says. It's much more difficult to say, is this a good response or a bad response? And this is what this off-topic low reliability is showing. So basically, we're showing that we have 2 classes of items, and one is very much more, or 2 classes of items to annotate. And even though the annotation instructions are the same, one class of items is much more difficult to annotate than the other. This is shown by the low reliability. The question, how can we have overall reliability, which is, how come this low reliability of the off-topic items, which are still, I don't know, maybe 40% of the data, a little bit more, how can it affect, how come it does not have an effect on the overall reliability? That's very similar to correlation. So because if you see all the red dots are at the very bottom, so even though people can't agree if these off-topic responses are, even if people cannot agree if these off-topic responses are a 1 or a 2 or maybe a 3, they agree that all of them together as a group are fairly bad compared to the most of the on-topic responses. And this is why it does not bring the reliability down by much. Another case of annotator, another case of item differences. This is a recent study. And here, this is actually no longer annotating verbal behavior, but annotating non-verbal behavior. So we have 2 annotators. Just mark smiles on videos. You take videos. I believe these were these were videos collected in so people talk. I think they would talk to a virtual character, and you videotape them. And now you want to see when do they smile, when do they nod, and maybe a few other features. But the important thing is smiles here. We found an overall respectable reliability, 70%. But you look at the reliability per video, and there's huge divergence. And this just means that smiles are easier to detect on some people than others. And once you think about it this way, then, well, it's not surprising. I mean, I don't think anybody is going to be blown away by this discovery. But these are the things that are washed away when you have when you report a reliability for the whole study. So is my procedure for annotating smiles, is it reliable or not? Well, generally it's reliable, but for some people it fails completely. So this is a case for looking at the individual items. A similar study, this I believe was YouTube videos. You also identify nonverbal behavior in videos, and this is this actually shows. Okay, so in this case, we identify again. I think it was smiles and head nods and several other gaze shifts in videos, and we wanted to see are people are experts. By experts, we mean graduate students. Are experts as good? Are people recruited on Amazon Turk? Are they as good as our in-house experts or not? So reliability, so you calculate agreement or reliability coefficients. And you found that, in-house experts have a certain reliability. I don't remember the numbers. But Amazon Mechanical Turk people were less reliable as a group, which is not extremely surprising. But now we had 3 Turkers, only 3. But now we say, OK, let's take the 3 Turkers and just do a majority vote, frame by frame. So the annotation is so you were looking at exact boundaries of when the smile start or where the gaze shift starts and ends. So frame by frame, if we have 2 people annotate, if we have 2 of them, 2 people agree that there is no smile, 2 or more, then we'll say there's no smile here. If 2 or more agree that there is a smile, we'll say there is a smile. Simple majority vote, frame by frame. The problem is, so this is a new instrument, right? It's not the same as just having a Turker. And we want to measure how reliable is this. So if instead of taking a Turker, if instead of taking a single Turker, I take 3 Turkers and do a majority vote, how reliable is this instrument? In order to do that, we actually need to have 2 instances of the same instrument. So we need to take 3 Turkers, calculate majority vote, another 3 Turkers, calculate majority vote. Now we can see how similar these are to one another. What's the agreement between these 2? For this study, we only had 1 instrument available. So we compared it to our in-house experts. And we found that the majority, so when we calculate how reliable the majority instrument is, the majority among Turkers, as opposed to compared to an in-house expert, we find reliability is comparable to that between the in-house experts themselves. About the same numbers. Whether we can conclude from this that the majority instrument among Turkers is as reliable as in-house Turkers, in-house coders, I'm not sure. So, to conclude, reasons to conduct agreement studies. And notice this, and this is, I wrote this before I knew about the Coherence. So I'm arguing here for reasons to conduct agreement studies, not specifically to calculate agreement coefficients. Agreement coefficients are a numerical tool that allows us to interpret some things within the agreement study. But the reasons we have to conduct agreement studies among annotators is one is to validate the schemes and guidelines, also to learn about how the annotators work, learn about the process of annotation. It allows us to identify patterns in the underlying data. For example, find out which kinds of items are difficult, which kind of items are easier to annotate. And they point out directions for qualitative studies, for qualitative analysis of the annotated data. And in all cases, results need to be interpreted. So while I do recommend using the alpha or kappa family as a tool, I think we need to go beyond reporting, saying, oh, I got alpha above 0.8, I can publish.
So I'm intrigued by your comment about the doctors who will look at the hedge words and read them with more certainty than others would. This is going to sort of feed into what I'll talk about a little bit after lunch, but it seemed to me that that's the kind of thing that really warrants some study, and maybe that's what you were getting at with your last comment about qualitative studies. My hypothesis there would be that that's a cultural phenomenon going on, where maybe things are written as hedge terms for all sorts of socio-technical legal reasons in a medical note, but the doctors know what they're saying, and so they can say, hey, yes, I know that says possibly, but what they really mean is probably or definitely. Do you have any feeling about that sort of thing? And can you account for that in models of agreement?
I don't know, I don't understand the last question of can you account for that in models of agreement. What we're having here is, you can think of it, I think you have two different populations of annotators, okay? So one thing that, and this is from the original paper, and it's a study that I've not been involved in, right? But one thing, so the original paper makes a claim that we like to think of linguist annotators as being experts. Now, what does it mean to be an expert? I can see that a linguist can be an expert in annotating, in tagging parts of speech. Yeah, my linguistic training is going to give me better knowledge. I'm better posed to say this is a particle, this is a preposition, for example. Or there are other cases where being linguistic expertise is right. But does being trained as a linguist help me? Does being trained as a linguist help me know what doctors mean when they say possibly or probably or could be or might be? I think the answer is no. I think for this you need to be well versed in a genre, and presumably people who are and again, why do doctors have a different understanding of these terms in their own medical texts? That may be a cultural thing. It may be just basically it's a different language use group, right? They're writing things among themselves, and they have their own interpretations, and it's different. By the way, the difference wasn't very big, but it was statistically significant. I think the point here is, I think the lesson to be learned from that is that expertise for annotation, the expertise required for annotation really varies by the kind of annotation you're doing. And there are some annotations there where linguistic training is really going to be good for you. It's going to really make you a better annotator. And there are other things, for example, interpreting hedges in medical text, that's just one example, where actually being a doctor is going to be better. Is the relevant expertise needed to understand the text better?
No, I agree completely, and I think that was part of my point, is to say, well, suppose you had this small effect with the doctors, and then maybe you want to have an annotation task where you have a larger set of things you're going to annotate, and some of the annotators are doctors and some aren't. The question is, could you then somehow correct for this difference?
I presume you could. I mean, if you can quantify it, then you can correct. Then I would guess you could correct for it. I mean, if you find a systematic relation. Again, I don't know exactly what they found in the study, so I don't know the exact data, but I would assume that you'd have to make a bunch of assumptions, right? You have to make the assumption that the population of say it's cheaper to get non-doctors to annotate. I don't know. That maybe it's probably correct. If you have once you've found the relation, and if you assume that it is consistent on the rest of the data, then you presumably could make some corrections.
Hi, so I guess the one thing I really wanted to object to in that talk is that I don't think consistency in the agreement sense is actually necessary, right? So you started by saying it's not a sufficient condition that people agree, but it's necessary. The examples that I was showing where people were systematically biased is a case where you don't actually need much agreement at all. As long as you have enough data that you can estimate people's biases. So you can take one movie reviewer who always gives a movie one more than the other movie reviewer. There's a lot of information in that, but they're not going to agree with somebody who's doing the right thing pretty much at all. So it's not actually, so you can actually apply techniques where you don't actually have much consistency at all, where you have very, very low agreement, but you can still extract a lot of information, right? And what you're going to see is when you go to these big ordinal tasks, I mean, you changed it to a scalar thing, but it's pretty easy to see that if you, instead of thinking about a 2-category task, you think about a 100-category task, like rate this on 0 to 100. right? Then we're probably not going to get much agreement at all, and you hedge that yourself by saying, well, you know, if they're all in the same neighborhood, that's giving you some information, right? So it's that same general principle. If everybody's in the same general neighborhood, and if their departures from the true answer are systematic, you can correct for that. So you don't actually need high agreement in order to infer the truth.
I think if I understand the objection, first of all, I agree that there are cases where you can have, a question is, okay, if you have an annotator that is consistently, you give an example, somebody always gives something that's consistently one above the ground truth, then you can, then there's a lot of information from that, and this I completely agree with, it's obvious. But another question is, and I think you also raised this in your talk, is can we even say that there is a real ground truth? With the number of labels and being in a neighborhood, I actually don't think this is, I'm not sure if you were getting at what I was trying to say. Even where your labels are from 1 to 5, there is a structure to the labels in that case. They're not just independent labels. And when we put and what I was trying to say, and what the alpha measure is trying to do by looking at the square differences instead of just saying same label, different label, what alpha is trying to do here is saying, look, there is a structure to the label. Let's use the structure of the label to get a more meaningful comparison than by just looking at these as completely distinct individual labels. And I'm not sure if this is what the methods you were proposing were suggesting, or if they can treat them as completely distinct. But if you think of labels, so the example where one annotator gives always one notch higher, or typically one notch higher, is easy to interpret. If you have an example where you really have non-structured labels, say a person who typically has nouns as verbs and verbs as prepositions and prepositions as adjectives, so typically tags it this way, then yeah, you also have a lot of information there, and which you can exploit, definitely. Maybe they just don't know the meaning of these words, of these labels, but it's much more difficult to interpret what the annotator is doing in that case.
Well, okay, I don't want to go into this in too length, but I think you actually can there. So we see that in the word sense data we're looking at, where there's like 20 word senses. There's no real ordinal scale there, but very often you see very systematic biases in some of the annotators. Like some of the annotators are fairly accurate with respect to the consensus, but they just missed one word sense. They just never annotated something with one particular word sense. Or they've conflated two word senses, like we know it's this, and they were just really confused. And you can tease that apart. And what happens is, by them being bad on a bunch of those cases, it sort of drags the agreement level down as measured by kappa. But the information is, there's still a lot of information in what they're doing.
Yeah, I agree with that.
Okay. Me again. So the other thing that I would disagree with in the things that you said is that meaningful agreement is the agreement above chance. I simply think that's wrong. You can have, so the example I gave was one where I was trying to explain why I think that's true. So the psychiatry example that you gave, it was very clear from looking at the contingency table, right, that there could not be good accuracy, right? There was good agreement, but it couldn't have been good accuracy there, especially on the diagnosis as positive having that condition, right? But you can have contingency tables that look very similar, right, that have high accuracy. So look at the case where there's a 5% prevalence of a particular condition, and in both the sensitivity and sensitivity of both annotators is 95%. What you're going to get is a contingency table that looks like 90, 50, 50, 50, right? You're going to get a kappa that's equal to 0, but the annotators are actually 95% accurate. right? They're not agreeing above chance, right? Because the chance, they're agreeing about 90% of the time. The chance agreement's about a 90% because of the bias in the task. And the agreement above chance, at least measuring chance the way kappa or alpha does, is 0. But I'd again say there's still a lot of meaningful information there. In fact, I don't think you're probably going to get better annotators for those kinds of tasks.
Okay. First of all, again, we don't know ground truth in the example I gave, but accuracy could be high, right? We don't know what the accuracy is. If really nobody was paranoid, then the accuracy on that one would happen to have been 100%.
Sure.
Yeah, I'm giving the example again of high specificity and sensitivity with low kappa?
With low prevalence, or high prevalence. It's all symmetric in all these things, so high, low, doesn't matter. You're going to get a kappa equal to 0, even with 95%. So you take 95% accurate annotators, 5% prevalence, right? You're going to get 0 kappa. You're going to get it all along that line. 10% prevalence, 90% accuracy will also be 0 kappa.
Right. I agree that there are cases.
So that's a case where I'm just constructing it, and I know the accuracy is good, and I know the kappa is bad. So there are cases where kappa can be bad, and accuracy. I agree in the case that we don't actually know, just from looking at the contingency table, what the truth is, but we do know agreement above chance can be low when accuracy is high.
This is actually, this is definitely correct, that you have, if you look at the literature on kappas from the I guess Cohen's paper was in 1960, published in 1960, and ever since, in every field that adopted kappa, you have these people who come up with pathological examples where kappa is counterintuitive to what they're trying to measure. So this is true of kappa. This is true of any other. It is true of almost any other single any time you try to boil a data set into a single number, single coefficient, you will find pathological cases where it just doesn't make sense, where the number doesn't make sense. I don't see this as an argument saying don't use kappa. It's an argument saying don't only rely on kappa. Don't believe that kappa gives you all the information. This I completely agree with. I still think that agreement is a useful tool in cases where you can interpret it.